其他的会尽量的。
因为目前可用的题目少于5题了，所以现在解开11题。
We would like to challenge number 4.
Number 4. You accept the challenge.
Honorable judges and worthy opponents, I'm the reporter from Team Examination, and today I'll be reporting problem number 4 on single disk. So first, this is our outline. We'll first start with the introduction, which is the problem statement, our focus, the phenomenon, and our setup. And next, we'll move on to our theoretical model, which we consider the vertical vectors, the horizontal vectors, and the free body diagram. And now, for the experiment, we'll do a preliminary experiment to exclude the unnecessary variables, and then we'll do the further experiments and to calculate the boundary conditions on whether the disk will float or not. So, as the problem stated, a metal disk with a hole at its center sinks in a container filled with water. When a vertical water jet hits the center of the disk, it may float on the water surface. Explain this phenomenon and investigate the relevant parameters. So our focus on this experiment will be mainly on 3 points, which is first explain the phenomenon, and 2 to investigate the relevant parameters, and 3 to determine its boundary condition. From the demonstration video, you can see that a normal disk just sinks into the bottom, and where there's a vertical water jet, the hole, it floats, and the water jet is gone and sinks again. And this is our experiment setup. We use a water pump inside of a transparent tub to make sure that the water flow is at a constant speed. And we use a vinyl tube to direct the water into, to make sure it's completely vertical to the plates. And we use multiple aluminum discs to conduct the experiments. And at last, we use ink, and I'll explain that furthermore later. So first, let's talk about our theoretical model. We can split this into 2 parts. First is the stable equilibrium. We can first calculate the force that's exerted on the plates. So we think the main force that's going downwards will be the plate's own weight and the impulse from the water stream upwards. And we think the main reason that it floats is because when the water pushes it down, it actually creates a height difference over here, and that creates water displacement for the buoyancy to allow it to float. And on the other point, we talk about the horizontal stable equilibrium, because from this the problem statement, if the hole is completely, the surface is completely flat, and it actually isn't stable horizontally, because if it's slightly tilted, it will have, the torque will push it the other way and make it sink. And this is our analysis for the forces on it. And we make sure that we make a little dent to make sure that it can have an equilibrium like this. And the dent is, the tilted angle of the dent is small, so we can ignore the difference from this. And one thing I need to clarify about if we're using the ink. As you can see, when we use the ink from the above, the water downwards actually just go down, and the water on the surface spreads out into the other direction. There's no flow under the disk. So from this, we can exclude a few phenomena. First is the Bernoulli's principle, because the water flow just goes down into the water sink. So the flow between the upward and the down is not the same streamline. So we cannot use Bernoulli's principle to consider it. And another point is about the Thorndike effect, because there's no water stream under the plate, so it cannot give it the upward force. First, for our preliminary experiments, we'll first talk about surface tension, because when the plate is going downwards, the water wall on the side is going upwards, so it should give it an upward surface tension. So we calculate the surface tension, and we also calculate the impulse from the stream and add it up with the total added up the weight into the total downward force, and we compare these two values, we can get that the total downward force is actually a lot greater than the surface tension. So we will, for simpler calculations, we'll first exclude this from our theory. Let's talk about the buoyant force. The buoyant force formula, as we all know, is the displacement of water, and it's related to the area of the plate and of the water and the air column on top. So the water displacement should be the air column height and plus the thickness of the plate. But however, when we're calculating the thickness of the plate, which is just h bottom minus h top, is only 0.03 centimeters approximately. So we think that is compared to the air column, it's significantly small, so we can exclude it from the experiment. And this, since we have varied the radius of the aluminum disc and cut several different discs with different surface area, we separated each model and calculated the results as shown. Thanks. And another thing I want to mention is about how we determine whether a plate will flow or not. And from the experiment, we can actually observe another phenomenon over here, which is the water stream going upwards and has a peak and going down. This is actually a phenomenon called hydraulic jump, and which is related to Froude's number. According to our reference, the definition of the Froude's number is that the square of it is the inertial force over gravitational force. In this case, the Froude's number will be the water stream speed divided by the square of g times the height of the water. And when the Froude's number is under 1.7, we cannot form a stable hydraulic jump, which is like a wall, something like this. So we can use this to determine whether a plane can flow or not. So for the boundary condition, let's first consider the lower limits. From the empirical formula that we got from the reference about Froude's number, we can actually get when the water spread out the distance and the relation between this distance and the maximum height of the hydraulic jump, which is in this form. We can actually observe that there is a gap between the two different separate lines. That's because we can't really explain that, but that's from the reference. So we approximate it into a red line, which we will use for later analysis. And in this one, we graph this with the graph we previously mentioned, and is the height required to flow that we previously measured. And then we put it together, we can actually get an intercept over here. So this is our lower limit for the boundary condition, which means that if the radius of the plate is lower than this value, then we cannot create a hydraulic jump, then it won't float. And next we'll talk about the velocity and Froude's number relationship with distance. Since the water is not there is viscosity inside of the water, and the plate is not perfectly smooth, there could be the flow speed of the water can slow down due to these few reasons. So we can, by putting a slide paper on top of the water and let it flow out, we can calculate the speed, the velocity of the water stream by the distance between the center, and we can calculate this into another graph about the distance, the relationship between the distance and the Froude's number, which we can get that when the distance away from the disk center is approximately 7.2 centimeters, which is the radius of the disk, the Froude's number goes to 1.7, which is our boundary limit. And when it goes past that, the Froude's number actually goes lower than 1.7. So the disk is larger than that radius, it will sink also. And that, so to put it in our actual experiments, we calculated, when we're doing the experiment, what we actually observed is that the plate radius, when it gets to actual, the radius to approximately 9.161 centimeters, it actually floats. We think that this error is caused by maybe the surface tension we ignored, because despite ignoring it, it still does some force onto it. And the bubble underneath the plate, despite the outer bubble's volume is actually a lot smaller than the air bubble on top, it could still cause some error. So now let's go into our conclusion. While buoyant force already provided an adequate upward force that can hold the aluminum disc vertical equilibrium, we realized that the main focus that we can realize that it's the hydraulic jump that actually determined its boundary conditions for the disc to be unsinkable. So by using the boundary condition we previously talked about, we can know that the range between how long the disc, or the radius of the disc in this range, it will be unsinkable, and which is also related to the water stream and other factors. And the dent in the center of the disc helps maintaining the horizontal equilibrium of the disc, thereby ensuring the vertical equilibrium by stabilizing the height difference of the air cylinder caused by the hydraulic jump. And this is our reference about the hydraulic jump. Thank you for listening.
Can you talk about all the parameters that you use in the experiment again?
Parameters. Okay. So first is the radius of the disc. Yes. And then we talked about, because we're only looking at whether the plate will sink or not, so we don't think that we control the water stream. And then we also control we look at the mass.
And did you consider about the height and water jet?
Yes, we do. We actually, because we have to measure. No, sorry. Let me rephrase. We use the water at a pretty low distance, so that we can consider that the floating speed is the same as the top. So we don't consider it.
Do you measure the height of the container?
Yes, we do. It's actually approximately 10 centimeters to 12. Yeah.
So you only use one measure.
Yes.
And for the water jet velocity.
How we measure it? Okay, we measure it through we pumped the water into a bucket with the same with the low height.
So do you have a figure? The figure of the water.
The video. Sorry.
So do you control every time you do an experiment is the same water jet velocity?
Yes, because every single time the setup is the same, and the pump stays at the same condition, so we assume that the water jet has the same velocity.
So for your experiment, there doesn't have any convection of the water that will or vortex of the water.
What do we have?
Vortex.
Action?
Under the container.
Under the container.
In a
Oh, you mean the water flow that's going? Oh, okay. We can explain it by the actual video we talked about previously.
So
The
you
one.
can explain it for video.
Yeah.
main focus should be the tuning of the phase and float and the reference parameters and the hydraulic jump. And overview the report. For observation part, he talked about the phenomena very clearly, and also the reference parameter is enough, and he have an extra consideration. And for theory part is the hydraulic jump and buoyant force and surface tension influence from the stream. And experiment part, he showed videos in the observation and also the height therapy. And the velocity and flow number is a relationship with the distance. And for the conclusion part, he said that no flow on the disk and hydraulic jump determined by the beyond condition, and also ensure the vertical injury by the stability height effect. And the point is for the strong part, have a very fluent energy and also a clear environment. And he explained his theory very clearly for the hydraulic jump formula and the flow number. And the weight is that of the parameter for the experiment. I think he can also do the water jet velocity and without clear conclusion. And now I'm going to discuss the part. And I will discuss about the hydraulic jump. And can you talk to me about why don't you consider the height? Why don't you consider the height of a container that will influence the experiment result?
You mean what height first?
The height of the container.
Height of the container. Okay. We'll go back to the beginning one. Same thing with this ink. The water we observe from the container outwards is actually just spread out underneath. So we don't think that there will be any forces that maybe bounce from the container upwards, or the conventional effect. This is
What about the height? The height of the container is more higher.
you mean if it's higher? I don't think we'll influence if it's less.
And do you think your experiment is only related to the hydraulic jump?
No, let me rephrase. The reason why we talk about hydraulic jump is to determine its boundary condition about how the plane can float. The real reason why we think about the plane can float is because of the buoyancy.
Can you turn to a page that you show the first diagram?
First diagram? This one?
And so hydraulic jump is here. And so you mean the which force is force?
The upward lift. We believe it's a height difference. Okay, if we don't consider the little water streamline here, it's not that considerable. The height difference will create a pressure difference between this surface and upward. Because under the same water surface, there should be the same pressure, and that creates buoyancy.
So it flows only goes by buoyancy.
Yes, that's our theory.
But I think the vortex will also influence
I don't really think so, because what we observed is that the water only goes downwards. It didn't really curls back. The water just goes, okay, maybe it's not obvious inside this video, but the water is over there. The black ink actually just goes.
related to a water jet velocity.
The water jet velocity? You mean?
If a water jet velocity is bigger, it will have a bigger vortex.
Okay, we will investigate about that.
And what do you use to make the disk stable?
You mean, okay, to make the disc stable, we actually made a dent over here, as this graph can show. If it moves slightly, it gives it a horizontal force to make it back to its original position.
If you don't give it this size to make it stable, then what will happen?
You mean what will
Will
happen
it
if there's
influence the
no?
hydraulic jump?
No, not actually. We don't think it would influence. Theoretically, the plate can stay stable, but it's not a static stable because if it moves slightly, it will tilt. And actually, from this, we can actually see some further interesting results about if there's no dent. Yes, from this graph, we can actually, because there's no dent and there's this slight movement, it will actually cause an oscillation. And that's what we're looking for.
Can you turn to the fourth target?
So which page exactly?
The page you just showed.
Oh,
Target.
this one.
This
Okay.
one. So you think about this will change the inner radius.
Yes, we do consider that it will change the inner radius,
If
but
you
we
change
don't.
the inner radius and the water just hits the area with the change.
Yes.
And what will happen influence?
The reason why we don't really consider that into it is because we didn't make the dent really big. It's just a slight tilt angle, so we can just ignore that.
Don't you think about it will change the velocity that's on the
Yes, it will.
surface?
Yes, we think it will. But that's in part of our effort.
What about the type of the hydrogen jump? Do you think what parameters make a difference hydrogen jump?
The hydraulic jump heights. Part of this side of hydraulic jump height is through the Throws number. And we can actually calculate it from the Throws number to know whether hydraulic jump will be
So in your experiment, the hydraulic jump height is always the same. Because of you said you didn't change
No,
the
no,
velocity.
it's not the same. It's not the same. I'm sorry, maybe I misunderstood the question. We can't actually calculate the height of hydraulic jump. We can only see whether it does have. You can only see from the gross number to see whether it has the hydraulic jump or not. And we consider when it's under 1.7, then we don't consider that as hydraulic jump.
We think that you should change the water jet velocity to find the limits that the system goes.
The water.
Water jet velocity.
The velocity over here is actually not the water jet velocity. We're actually talking about the velocity horizontally. And for the water jet velocity, we will.
And another question is that what's your hydraulic jump radius?
Radius.
So the radius is bigger than the base radius.
I mean,
The hydraulic jump
hydraulic.
radius.
Oh, you mean I see. Do you mean that the hydraulic jump radius is like this radius? Is that what you meant? We don't think that is one of the things that we consider because the way hydraulic jump works is that when the speed changes and then it changes its kinetic energy into potential energy. So at this point it tilts upward. So this is the place where hydraulic
Can you
jump.
imagine which situation will make the hydraulic jump radius smaller?
Hydraulic jump radius smaller. We actually think that there's a limit to the hydraulic jump radius, which we talked about in our boundary conditions. This is the Throws number relation to the distance away from the center. So if we want the hydraulic jump to perform, it has to be longer, but it has to be shorter than this distance, or else under 1.7, it will create an unstable flow.
Why don't you use the Bernoulli principle? Only because of it didn't same.
The reason why we don't consider Bernoulli principle, as I previously mentioned, is because the way Bernoulli's principle works is inside of the same streamline, and we don't think that this is a water jet and this is the other water top. We don't consider this as the same.
And what about you use the Bernoulli principle on the surface of the water?
On the surface of the speed difference between these two. The reason why we can't really exclude that is, as I mentioned, because we don't think these two are the same. They are not in the same streamline.
Or maybe you can use Bernoulli's principle only in this place.
Only in this space. You mean between the water and air?
And the height of hydrogen gas.
So you mean that only a fall? But I think that the main reason that it's lifting is because of the buoyancy upwards. And if this creates a pressure difference between the water stream, then it should affect under distance.
Have you measured the velocity of this place and this place?
Yes, we do. We measure the velocity of this by we place a tiny piece of paper and put it on top of the water stream and use tracker to track it and to see how fast it flows. Because we know the distance, and then we can come up with this graph.
So which place have a bigger velocity?
The velocity should be actually at its maximum when it's closer to the center because of the friction on the plates and the viscosity of the water.
Do you mean the velocity will
It will decrease.
It will decrease.
And after that, it turns into potential energy.
So the energy translation is from
The energy transformation is from when they chat the potential energy and kinetic energy when it hits the plate, separates, and it turns the potential energy and kinetic energy into just kinetic energy on the surface of the water. And this goes on. Underneath it, we don't think that the water stream underneath it really is affected by this water stream. Because from our observation, we only see that the water is flowing downwards.
do you do the parameters of the inner radius of the inner radius?
Inner radius. We don't mean the inner radius of this. When we're calculating the impulse from the water, the area we calculated is actually the outer radius area minus the inner radius. So we only consider the point where the water touches.
For next question, and can we talk about the container again?
The container? You mean why I don't think it will affect? Okay. The reason I think that the container won't affect is firstly, our theory is mainly on buoyancy. The buoyancy force is only related to whatever displacement on top of here.
So if your container's height will, if the height is higher, and the buoyancy will.
The buoyancy doesn't affect. That's what.
So do you think the tangential force driver?
This one?
So the force can make this balance only for the pressure force, only for pressure force and the ground force and the up force and
There's.
Hey, yeah.
Thank you.
For summary of the report, summary of discussion, and we discussed about the height of a container, and I think the height of a container will affect the vortex. And also we discussed about the hydraulic jump, and the hydraulic jump height and hydraulic jump radius. And I think they will have a different situation if the hydraulic jump radius is bigger than this radius, and the other situation is the radius of the disc is smaller, is bigger than the hydraulic jump's radius. And we mainly talk about, also we talk about the velocity of the water jet. I think if the water jet velocity is bigger, and we can make the heavier is roll under.
There's some question for both recorder and comment, and I want to ask, do you think the velocity of water above and below the third will change?
Yes, they're different.
And do you think it can affect the result?
No, we don't think so, because we don't think that they're in the same stream line. So that the one is proportional
difference is right.
Yes.
So I can make no reserve.
Oh.
And so I want to ask what's the difference between this and this?
We believe it's actually it serves the same purpose. Oh, actually, this is just for modeling. The actual one we use is this because this one actually it made. Okay, this is our fault. We shouldn't make a picture like this because it actually could create another force stream on the other direction.
Another question is that for operator video, yes, for this one, I want to ask what causes the vertical vibration in the video?
The vertical vibration.
Yes.
We actually just think that it's because of the initial condition of the plate. Because at first, the plate is on top, and when you push it downwards, it actually pushes it a lot more downwards. It's like an oscillation in the spring. Even if you put it avoid in a certain force, it actually oscillates because the force at first happens to it. So we think that it's just an oscillation. It doesn't really affect the results.
What causes the vertical vibration in this video? Vertical vibration. Yes.
That's also the vertical vibration. And I think the flow can, it can two parts. The first part is it will go on one surface, and the other is it will go down, it will go upward.
Thank you.
rate of the water jet uses to try and to find the lower limit that just gives a metal disk enough for the frequency. And the summary for the report, we have the understanding of the problem and define the boundary condition and the vertical parameters and the vertical and the horizontal models. And for the theoretical analysis, the vertical and the horizontal process and free body diagram and the impulse from the stream. And for the experimental confirmation, they have the boiling down course and the hydraulic jump for the peak, and it causes the lower limit. And for the recorded pros and cons of their introduction to the problem and of the video, and they use the surface tension, total force analysis, and the viscosity to quantify the result, and the experiment to verify the theory regarding gradient force and the hydraulic drum, and for the constant address of physical phenomena of the rotation, and no theoretical consideration in it is the energy transformation, and the lack of investigation on the water flow and the strength of the stream, and they have a lack for comparison between the theory and the experimental data. And here's a summary for the opponents, and they need more explanation on the experimental data and they don't have enough physical explanation. And for the pros and cons for the opponents, they have the clear questions and understand the experiment well, and they have sufficient use for the association time, and they legitimate the question based on the further understanding of experiment and parameters. And for the cons, they have lack of comments on the reported and they did not focus on what the reported say for the theory. And for the discussion analysis, the opponent asks about how will the height of the container affect the motion, and the reporter responds they don't think that will affect the result. And we agree with the reporter, it will not affect that much and can be ignored. And the opponent asks what do you use to make the disk stable, and what's the influence, and the reporter answered that there's nothing that will cause the instability. And we think the instability of the disk should be taken into consideration. And for the opponent asks that what parameter makes a different hydraulic drum, and the reporter responds is to calculate the real number, and we do not consider that under some conditions, and we agree with reporter. And to the miss point, they didn't consider the stability of the flow using in the experiments, and they didn't consider the spinning of the disk, and they didn't quantitatively measure the measurement of the strength of the stream, and they didn't consider the height of the container and the velocity of the water flow. Because I think the velocity of the water flow may affect the force that's on the disk. So here's for my review. Thanks for your kind attention.
For the completely revised, I have a few points that I want to mention. First, our theory is mainly based on buoyancy, gravity, and the impulse from the water, which will reach vertical equilibrium. And we think that it's the depth that of the disk that creates the horizontal equilibrium. And the water flow will just go through the hole and not affecting the other system. And hydraulic jump actually determines its boundary conditions to be unsinkable. And about the Bernoulli's law, we think that it can be ignored because the water above and below the disk are not in the same stream. However, I think to improve it, we can actually calculate the pressure difference if the Bernoulli principle works. We put it into our calculation and compare with our results to further improve it. And we don't think that the container affect the results, since we only really consider about the buoyancy, and the buoyancy is only about the displacement of water above, and we think that the water going downwards is that actually it doesn't really affect how the water flows underneath it. And thanks to the reviewer and the reporter, I think we all learned a lot more about this topic today. Thank you.
Any questions?
Any comment if the diameter of the center hole on this is larger than the wall?
I think that, okay, we actually did an experiment about this, but we're sorry about that we didn't put it on the PowerPoint. What we observed that it would just sink to the bottom.
for this phenomenon, I find there is a vortex under the water, and the disk can float.
I think maybe it can flow if the diagram is small enough and almost with the water flow.
Any more questions?
Do you think that the discrete areas have the influence on the flow?
You mean whole area?
Yeah, whole area.
Yes.
So not whole area, so the discrete area, not the whole area, not the central whole.
Oh, you mean in the outer?
Yeah, on the.
Yeah, we talked about it using the boundary condition, the hydraulic jump. We think that because whether the hydraulic jump can form actually related to whether the distance of the water traveling. So yes, we do think that it matters.
Okay, thank you.
Thank you.
Important. 8.9, 8.8. The bottom. 778, 78. Viewer. 76, 777.